Sampling distributions are the key to statistical inference. In statistical inference, we use sample data and sample statistics to draw conclusions about populations and their parameters. In order to do that effectively, we have to understand how statistics behave, and the sampling distribution of a statistic will tell you how a statistic behaves. It will tell you what values the statistic can take on and how often it can take on those values. And with that information, we can go a long way toward doing effective statistical inference. To get started, though, we have to think about the distinction between parameters and statistics. Parameters are numbers that describe populations. A parameter is a fixed number. It's not random. And population parameters are generally unknown. And that's why we have to do statistical inference. We don't know what the parameter value might be, so we use sample statistics in order to learn about those parameters. Statistics, on the other hand, are numbers that describe samples. If you draw a statistic from a random sample, it's going to vary from sample to sample. That statistic would be a random variable, and its value would be determined by the particulars of an individual sample. But since they vary from sample to sample, these statistics are subject to what we call sampling variability. They're not always going to take the same value. However, you can figure out the value of a sample statistic because you have the sample data from which you calculate the statistic, and so that's a number that's known. Then you use this known value, the value of the statistic, to answer questions about possible values of the population parameter. And here are a few distinctions and some terminology you need to be aware of. There are different measures that we look at in statistics, such as means, proportions, standard deviations, and correlations. When we're talking about population parameters, we use a specific set of notation, and when we're talking about sample statistics, we use an alternative kind of notation. So for a mean, the mean of a population is indicated with this Greek letter mu, whereas for a sample, we use x bar to indicate the sample mean. And these would apply in situations where we're working with quantitative data. If you look at a proportion, in a population, the proportion of the population that has a given characteristic would be this lowercase letter p. And in a sample, the proportion of the sample that has that particular characteristic would be written with a p hat. So this is pronounced p hat because it's got a little hat on top of the p. These would apply in situations where we're working with categorical data. An individual in the population or in the sample would either possess a particular characteristic or not, and so you can categorize the individuals in the population or in the sample in terms of whether they have, a particular characteristic. And this proportion p with no hat on it that applies to the population would be the proportion of the population that has a characteristic, whereas over here this p hat would be the proportion of the sample that has a characteristic. So it's important to keep this in mind when you're talking about your data. Means would apply in situations where you're working with quantitative data, and proportions would apply in situations where you're working with categorical data. You've seen the standard deviation, sigma, for a population versus S for a sample, and the correlation rho, Greek letter rho, for a population versus the correlation R for a sample. Statistical inference is about using sample statistics to draw conclusions about population parameters. There are two kinds of inference that we generally do. One is to estimate parameters using what we call a confidence interval, and we'll look in later videos at how confidence intervals are generated and how they're interpreted. The other way we answer questions about population parameters is through tests of significance, which test claims about parameters. And those are the two main kinds of inference that you're going to be doing in the near future. Now, a sampling distribution basically comes from, it's hypothetical. Suppose you were to draw a simple random sample of size n from a given population and calculate a statistic from that sample data. It could be a sample mean or a sample proportion or some other statistic. And you repeat that process for all possible simple random samples of size n from the same population. That is, we're going to generate at least hypothetically generate every possible SRS of that given size from that population. These will give you a whole set of possible values for the statistic, and that distribution, all the values that the statistic takes on and how often the statistic takes on those values, is what we call the sampling distribution of the statistic. Now, when you describe a sampling distribution, you talk about the same old things that you've always talked about when you describe distributions: center, spread, and shape, any deviations from the overall pattern, and basically it's just a matter of describing a sampling distribution the way you would describe any distribution. Some statistics have a nice quality that the mean of their sampling distribution is equal to the parameter that the statistic corresponds to or is being used to estimate. And a statistic that has this characteristic is called unbiased. It's not always going to be equal to the parameter. In repeated sampling, the statistic will take on a variety of values, but these values will be just randomly different from the population parameter. They will not be systematically different. So if you have these random deviations that are not systematic, then the statistic is unbiased. And it's a very valuable characteristic in a statistic, and it's something that you want to design your data gathering process so that you can reduce or eliminate bias as much as possible. Variability, on the other hand, is this tendency of sample statistics to take on different values in different samples. This is going to depend on the sample design and the sample size, as long as the population is much larger than the sample. The way you can reduce variability is by increasing your sample size. Larger samples tend to yield estimates that are closer to the true parameter, so they're going to be more accurate, less variable, and going to allow you to make much better estimates and answer questions about your parameters to a much greater extent. So if you can reduce variability, that's a very good thing. So bias is generally something you want to try to design out of your whole data gathering process and all of whatever formulas you use to generate your statistics. If you can do that, then you can reduce variability by increasing the sample size and have the best of everything. But there will be trade-offs because larger samples cost more than smaller samples, and so you're always going to be faced with that kind of trade-off whenever you think about increasing your sample size.